Hi, my name is Leonardo Frid and I'm going to be leading you through this brief tutorial on simulating spatial events in STSIM. This tutorial follows on the tutorial called Spatial Models in STSIM and uses the material generated in that tutorial. For this tutorial, make sure that you're using STSIM version 3.0.34 or later. We'll be covering a number of topics, including a brief review of the previous tutorial material, looking at the files that make up a library for spatial model runs, and running spatial simulations using size distributions. Now to begin the tutorial, open up your browser and navigate to synchrosym.com. This website is the documentation site for SyncroSym and STSIM, and on the left there's a link to tutorial materials. On this page you can see videos for all of the tutorials that we develop. And under the previous tutorial on spatial models in STSIM, there's a link to download the files generated as part of the tutorial. So I'm going to click on that link now, and the file is downloading. And I'm going to show that file in a folder and right-click on it to extract it. And I'm going to extract it to my documents. Now in my documents, I'm just going to sort by date, and you'll see there's actually three files or three units that were included in that zip file. First of all, at the top we've got STSIM spatial tutorial.ssim, which is the STSIM library file. And underneath that we also have two folders, a .input and .output folder with the same name. And these folders contain the rasters that are used to generate both spatial inputs and spatial outputs for the model. Now I'm going to open up STSIM by clicking on the link in my shortcut bar down here. And I'm going to open up that library that we just downloaded. Okay. And so before we get into creating new material, I'd just like to briefly review some of the material that we went over in the previous tutorials. And so to do that, I'm just going to go again to the paper that describes the methods in STSIM for state and transition simulation models. This was published recently in Methods in Ecology and Evolution. And scroll down to the first figure, figure number 1, which shows the simple model that we developed in the previous tutorials. Now this is a model where a forested landscape is represented by three possible vegetation states for any one location in that landscape. And those states are deciduous in yellow, mixed forest in brown, and coniferous forest in green. So at any one point in time, a cell in the landscape must be in one of these three states, and that cell can transition to other states according to three possible transition pathways. Succession, either from deciduous to mixed or mixed to conifer. Fire, either from mixed to deciduous, conifer to deciduous, or there is a possible pathway not shown in this diagram which would transition deciduous back to itself. And fire resets the age of a cell to 0. And finally, in purple, transition or forest timber harvest, which transitions from conifer to deciduous, and again resets the age of a cell to 0. So with an initial state and age for each cell in the landscape, we're able to use this model to track changes in states and ages for cells over time. So I'm just going to make this figure a little bit smaller and scroll down so we can see it alongside our model on the right. And so now in STSIM, in the previous tutorial, we looked at organizing scenarios inside folders, and we have a non-spatial folder that contains the material developed in the original tutorial. And then we have a spatial folder where we simulated a scenario spatially, and we're able to generate maps of outputs. And again, just to go over some of the scenario inputs, I can either double-click on the scenario or right-click and select Open. And and we've got a name for the scenario, we've got an author, and we've got a brief description. Under run control, we specified that we wanted this scenario to run for 10 time steps and a total of 10 Monte Carlo iterations, and we also specified in the previous tutorial that this would be a spatial run. Under transition pathways, we see a similar diagram to what we have on the right, with each cell on the landscape being able to be classified as either deciduous, mixed, or coniferous forest. And the transition pathways themselves that represent the changes between cells are drawn on the diagram, and we can find out more about them by, say, double-clicking on one of the boxes. On the conifer box, we can see that the conifer can transition to deciduous either because of fire, with an annual probability of 20%, or transition to deciduous because of harvest. And the probability is not set here, we just have a value of 1, but a minimum age of 40. And I'll explain why we have a value of 1 for timber harvest shortly. The other thing to note is that we artificially bumped up the fire probabilities by a lot just so that we could see sufficient amount of fire to demonstrate some of the features in the model. Another way to view the transition pathways is by just clicking on the probabilistic transitions tab, which shows you a list of all the transitions that are possible. Now again, to explain why we use the probability of 1 for harvest, if I click on the transition target tab, you see that here we're telling the model that we'd like to harvest 20 acres per year. And so rather than using the probabilities, the model uses this target. We also define how we want to initialize the landscape at time 0. So we told the model we wanted to simulate a landscape that's 1,000 acres in size with 1,000 simulation cells, meaning that each cell would be 1 acre in size. And when initializing the landscape, we asked the model to assign the state and age to a cell according to this distribution shown below, where 20% of cells are coniferous between 20 and 100 years old, 40% are deciduous between 0 and 10 years old, and 40% are mixed between 11 and 20 years old. We also specified, because we were running a spatial model run, that we wanted both non-spatial summary output for state classes and transitions every time step, and state classes, transitions, ages, and the average annual transition probability spatially, so rasters for these. The top 3 we wanted every time step, and the average annual transition probability we wanted every 10 time steps. So when we ran the model, and I'm going to add this to results by right-clicking on it and saying add to results, we looked at both output in terms of how much area there is in the different kinds of forest over time, and the proportion of the landscape undergoing different transitions over time as well. But we were also able to look at maps of output. So for example, a map of transitions. And this shows 3 kinds of maps over time where we see cells transitioning due to fire, harvest, or succession for different time steps. And if you recall, the one thing that jumped out at us is that the cells don't appear to be interacting with each other, and indeed they are not. We're applying transitions probabilistically 1 cell at a time. And so you might expect that in the real world this would seem unrealistic because, say, for example, a fire might initiate in 1 cell and spread to its neighbors as part of a single event where cells are interacting with each other. And so that's what I'd like to be able to show you in this tutorial. And again, if you go back to the paper on the right, on the state transition simulation model methods, if you look at figure 2, one approach to doing this is by using some kind of external model that essentially defines where particular events are going to be happening. And in this example, we have an external model defining the location of a particular fire event and essentially setting the probabilities of fire to 0 for that particular time step for most of the cells, but to 1 for some of the cells. Excuse me. So in STSIM, there are some built functions to be able to model this kind of event. And that's what I'm going to be showing you how to use in this tutorial. So I'm going to close the maps now. Oops, I didn't mean to maximize it. I meant to close it. I'm just going to hit the Arrange All button. We can leave the chart open for now. And what I'll do is I'm going to right-click on the scenario generated in the previous tutorial, select Copy. right-click on the same folder and select Paste. I'm going to open that up, and I'm going to rename it. And I'll call it Harvest 20 Acres per Year with Size Distribution. We'll call it with Fire Size Distribution. And what I'll do then is under Advanced, Transition Spatial, there are a number of features that allow us to define some built-in approaches to allow cells to interact with each other. And for this one, we'll be expanding the node called Transition Size and selecting the Transition Size Distribution input screen. And so here for fire, what we'll tell the model is that we expect about 10% of fires to be somewhere between 0 and 1 acre in size. So essentially 10% of fires will be represented by a single cell, whereas in the previous model run, 100% of fires were represented by a single cell. But we want fires ranging from 1 acre to 10 acres to represent 20% of fire events. And we want fires ranging in size from 10 to 100 acres to represent 40% of fire events. And so the remaining 30% of fire events will be between 100 and 1,000 acres in size. And so now the model will, built into its algorithm, be generating events that follow this particular size distribution. I'm going to close the scenario window, and now that we've generated the size distribution input, I'm going to right-click on my scenario and select Run. I'll be prompted to save, and I'll say yes. So we see the progress of the simulation happening here. And while the simulation is running, I'll just let you know that in future tutorials, we'll also be showing you other ways in which you can specify probabilities for cells in space. And one way of doing that is by bringing in data from either an external model or from a retrospective analysis for a particular landscape. I'll talk a little bit more about that at the end of the tutorial. So our simulation run is completed, and we can see that we have similar patterns in terms of the amount of area in each state class and also in terms of the amount of harvest and succession. We have similar pattern in terms of the amount of fire, but we see that there's a tighter fit around the amount of area undergoing fire for this recent run that we did that's represented by the scenario in red. Now I'm going to show you the maps, and again comparing these two scenarios, let's look at transitions. And just to make it easier to compare, I'm going to only show the fire transitions and select Apply. And you can see that over time, the scenario that we originally ran is simulating fires as single cell events, but the scenario that we just ran over time, you can see some time steps have more than one fire, but they're generally following a pattern in terms of typically seeing mid to large size fire events occurring in this landscape over time. And this is for a single iteration. Again, I can toggle to different iterations at the top of the chart window. And to observe what that might look like in terms of the overall probability of fire across all time steps and iterations, I'm going to show you the fire probability map. And so again, we can see a much more aggregated probability of fire for the second scenario that we ran as opposed to the original scenario where cells were not interacting with each other. And that also in itself will have an outcome in terms of the resulting pattern for transition states and ages over time. So I'm just going to hit the arrange all just to be able to organize the maps, and this is the map that I want to show you. And again, if we scroll over to the far right, we'll see that for the original scenario, we see a much more scattered pattern in terms of the states and ages. And for the scenario that we just ran with transition events, we see a more aggregated pattern. So that's the end of the feature that that's going to be demonstrated in this tutorial. In the subsequent tutorial, I'll be showing you how to load external spatial data as model inputs, and that will include loading spatial rasters to represent the initial conditions of your landscape, and also spatial rasters to represent the probability of events occurring for individual cells. Thanks for listening.